Howdy, howdy, this is Mr. Potter. What we're going to be talking about in the next couple of videos is dealing with this idea of interconnected computers, networks, and routers, and servers, and what is the most effective way to connect these computers together so that we can transmit messages as effectively as possible. We don't want to add too much infrastructure cost, but we do need to allow to make sure that a message can always get somewhere if possible. And so we're going to start by talking about the idea of a minimum spanning tree. So I want to start off with some situation, just kind of explain what's going on here. We're going to be talking about some terms such as nodes and edges. So when I talk about nodes, I'm talking about these circles that we see here and here. And when I talk about edges, I'm talking about the lines in between. And in general, we don't want to draw them so that the lines are crossing because it makes it ambiguous as to whether or not right here there's some type of connection between them. So here I have A is connected to B, A is connected to C, A is connected to D, B is connected to C and D, and C is connected to D. I can always take some diagram where I've got these signals crossed and rewrite it as some type of diagram where the lines aren't being crossed. So here A connects to B, A connects to C, A connects to D, B connects to C and D, and then C connects to D. So I can rewrite this symbol as a symbol where it's less ambiguous. And it's going to be helpful for us to think in terms of this less ambiguous because I don't want to deal with the situation where I think two lines are crossing means that they're connecting, because that's going to cause issues with us. So when I'm talking about these minimum spanning trees, there's certain notation that I want to use. So a node is going to be a place where lines connect to each other. These nodes are the objects that we're dealing with. So there are servers in our case, or our routers, the computers that make up the internet. And then we also talk about edges. And the edges are these wires that are connecting the computers on our internet. So when I look at this, I'm looking at some type of cost. And the thing is, each one of these line segments is going to have some cost affiliated with it. Like it might cost $2 million to connect these two servers in different cities with a permanent cable that's going to do it. Whereas over here, because this is a shorter distance, maybe this only cost $1 million, and because this is over really rugged terrain, this may cost us $5 million. So each one of these edges has some type of cost attached to it. And because we're talking about a minimum spanning tree, I usually want to try and minimize the overall cost of the system. Now keep in mind, I'm not trying to minimize the distance traveled because we are talking about messages that travel at the speed of light. I want to minimize the overall cost, the overall weight that we're talking about here. And there are two things that we are looking for. One thing that we want to have and one thing that we don't want to have. The idea of a cycle is I'm going to have some nodes that are connected with more than one path to each other. So in other words, if I want to get from this node to this node, I could travel along this path or I could travel along this path. And so this is considered a cycle. What I would really prefer is a tree. So the idea is that there's only one path to each of these nodes, either down this path or down this path. And so we call these a tree because there's usually a very set defined path. There's not more than one path. So I could see myself being able to eliminate this to create a tree out of a cycle. And that's really the key that we're looking at here. Keep in mind that when we're talking about a minimum spanning tree, we're talking about three things. When we talk about minimum, we're talking about we want to have the lowest possible cost. When we talk about spanning, we need to make sure that every one of these circles is part of our path, is part of our circuit, is part of our connection. There's no server that's left out. And when we talk about a tree, we're saying that we do not want cycles, because if I have a cycle, I can always eliminate at least one path to transform that cycle into a tree. And eliminating a path is going to decrease the cost. So here's our minimum spanning tree. So let's go over to an example of this. So we've talked about what a minimum spanning tree is. I need to make sure that we cover all the nodes. That's the spanning part. I need to make sure that it's a minimum so it has the lowest total cost. And keep in mind when I'm talking about the total cost, I'm not saying the shortest path. That actually is something that we will address later. I don't necessarily want the shortest path. It's okay to have a long path as long as I've covered all the nodes I can get from any one node to another node. And I want this to be a tree because I don't want a cycle. So these are the things that I'm looking for when I talk about a minimum spanning tree. So I want to find a solution to this minimum spanning tree. And so I'm looking at this, and I'm going to switch to my highlighter here. There are several ways that I could look at this. One way is say, well, I know that this is probably going to be part of my tree here. So there's $1 million there. I know that this $5 million is probably not going to be part of my tree because I could see just having the $2 million and the $1 million and I wouldn't need this path. So this looks pretty good. And now that I've got this, I need to pick one of these, but I don't necessarily want both. So we'll just arbitrarily choose one of these. And then we have a path here. This path here, this path here, and this path here. And we've eliminated this path here and this path here. So these yellow paths form a tree. The question is, how do I know that this is a minimum spanning tree? The question is, how do I know that it's the minimum? I mean, it certainly looks like it's the minimum. It certainly involves the 3 lowest costs, and it certainly spans all the trees, so it looks like it might do it. The question is there a technique that works all the time? And that's one of the things that we're going to talk about. We're going to talk about Kruskal's algorithm. Now, the idea with Kruskal's algorithm is the first thing we're going to do is to put all the costs in order. So I've got a 1, and then I've got a 2, a 2, a 2, a 2, and then a 5. So I've put all of these costs in order. The second thing that I'm going to do is I'm going to start with the lowest cost. And add it to our path. So right now I'm looking at this, and the lowest cost that I see is this $1 million. That means this $1 million path should be part of my path because it is the lowest. And what I want to do is I want to continue adding paths in cheapest first order. But the idea here is that I do not want a cycle. So I need to make sure that when I add a path, I make sure I don't add a cycle. So I'm looking at this, and I want to add a 2, so I'm looking at this 2 here, and I could add this 2, that would be fine. I could add this 2, that would be fine. But now if I try and add any of these other 2s, if I try and add this 2 down here at the bottom, that's going to cause a problem because now I've got a cycle. And I did not want that. So I don't want to add this path down here. If I add this path here, then that's going to create a cycle as well. So I'm not going to want that path. Oops, I did want that. So I really can't add either of these 2s, and if I add this 5, that's going to create a cycle as well. So at this point, this is a minimum spanning tree. Notice that it is a minimum because my cost is 1 plus 2 plus 2, which is $5 million in this case. That's the smallest this could have been because I added the 3 smallest numbers in my list. Does this span? Well, A is part of this loop, B is part of this, C is part of this, and D is part of this, so yes, it spans. And is this a tree? Well, part of what Kruskal's algorithm did was it made sure that I never actually had a cycle, so I always avoided cycles, so yes, it is a tree. So I've got a minimum spanning tree because I have minimum cost, I span all of my nodes, and I do have a tree, not a cycle. So that's the idea behind this. And of course, keep in mind when I'm looking at this, things to watch out for. I do not want a cycle. Okay? I do not want to have any type of cycle because if I have a cycle, I clearly could eliminate one path and all of these nodes are still connected. This is still spanned if I get rid of this one node. So the idea here is that, I should get rid of the largest node, or the largest edge, I should say. So if I have a cycle, I'm going to want to get rid of the largest edge. That's one thing that I need to look out for. And the other thing that I should really watch out for is that if I have n nodes, they need n minus 1 edges. Because between every 2 nodes there should be an edge, but 2 nodes is going to give me 1 edge. 3 nodes should have 2 edges. 4 nodes, which is the example that we did in our previous slide, had 3 edges for it. So we notice this pattern here. 4 nodes gives us 3 edges. If I was dealing with 5 nodes, then I really should have 4 edges. So whenever I have n nodes, I should always have 1 less edge than the number of nodes that I have. So I'm looking at this, and when I'm considering nodes to add to my tree, I always want to look at the lowest cost first. That was part of Kruskal's algorithm to make sure that I put these costs in order and I approached this one first. Then I went to the next highest. And that makes sure that the lowest costs are always being added. That's going to help me with the minimum part of our minimum spanning tree. So that's Kruskal's algorithm. I want to do one more example of it. So here is a larger problem. So I've got a lot of different nodes. I've got a lot of different edges, and I need to make this work. Keep in mind that I have 1, 2, 3, 4, 5, 6, 7, 8 edges. So 8 edges means that I have 8 nodes. Horrible. I have 8 nodes. That means I need 7 edges. So remember, the first step that we do is we put these in order. I've got a 2, a 2, a 2, a 2. So I've got 4 2s. Then I've got a 3 and a 3. So I've got 2 3s. Then I've got a 4 and a 4 and a 4. Then I've got a 5 and a 5 and another 5. And then I've got a 6 and a 6. There are a lot of extra edges that I don't need, clearly, because I've got more than 7 edges. But I'm not just universally going to pick all of the 2s because I may end up with a situation where I end up with a cycle. I have to pick one edge at a time and then see if that makes a cycle. So I'm going to start with one of my 2s. So here's my first 2. Looking from left to right, there's my first 2, and that's perfectly fine to choose. My next 2, well, I'm looking at this one here, there's my next 2. Here's another 2. Hasn't formed a cycle yet. Here's another 2. That hasn't formed a cycle yet. Now when I look at this 3 looks good. And this 3 looks good as well. Now keep in mind I want 7 edges. I've got 1, 2, 3, 4, 5, 6 edges already. And notice that every node is currently touched with the exception of this one. So now let's look in order. If I look at this first 4, let me change to a different color. If I look at this first 4 is probably going to be this node here, but notice that so this edge here, if I add this edge, then I've got a cycle that starts here and goes around like that. That is something I don't want, so I'm going to get rid of that. That's a bad edge. If I add this 4 here, well, that works. That gives me something that I want. It doesn't create a cycle, so I'm going to go ahead and make that one of our good edges. And by the way, that puts us at 7. If I look at any of these other ones, well, I've got a 4 here that I could add. If I add this 4, then I have a cycle here and here, so don't want that. If I look at the 5, well, I've got a 5 here, but that's going to create a cycle here. So no, don't want that. I've got a 5 here, but that would create a cycle as well. And if I look at this 5 here, that's going to create a cycle as well. And then I look at my 6s here. This 6 would create a cycle, and this 6 would create a cycle. So the idea of us using Kruskal's algorithm is to make sure that we're not guessing our way through it, that we have an algorithm, we have a procedure that has very defined steps, successes and failures, yeses and nos that are given to us formulaically, not just guess and check. And this gets us a minimum spanning tree. Notice that for our minimum spanning tree, our total cost would be 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Our total cost would be 18. That means that each one of our servers, including this one here, which we just finished with this last 4, is covered using a minimum number. We didn't have to use any of the 5s, we didn't have to use any of the 6s as part of our path. So what you're going to be doing is you're going to be going back to studio.code.org. So let's go ahead and go to that website real quick. You're going to be going on to stage 6, and you're going to be looking at these choices. And there's going to be some information here about the vocabulary. So you're going to need to know what is a graph, what is a node, tree, cost, cycle. And you're going to go through some diagrams here. So you're going to have to do some matching. So notice here, A, it's talking about what is this whole thing. This whole thing is a graph. What is B? B is what it is. And here's matching with some of our vocabulary. Then we're going to jump to our next thing. It says, what does a minimum spanning tree tell you about a graph? And there's some choices. One of these is the correct answer. And then on step 4, the question is, which one of these is a minimum spanning tree map? Some of them are obvious. I mean, this one should be pretty obvious here, E, because it's not a tree, it's a cycle. But all of these other ones, excuse me, A, E, and D, A, C, and D are trees, so the question is which one's minimum. And notice what it says here, the distance between 2 points is depicted by the number of line segments connecting any 2 points. In other words, the number of dashes that you see here, the number of dashes here, this is going to be a 1, and this is going to be a 3, and this is going to be a 2, and so forth. So you're going to look at the number of dashes to determine the weight, and you're going to find out which one of these is a minimum spanning tree. So, have fun with this. Use this to your advantage. We're going to continue using this idea of graphs, nodes, and edges in our next lesson. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.